Here's what we plan to do today. I'm going to finish up on this idea of NP completeness and NP reduction and give you the hints you need to finish problem 2 on the homework. And then today, most of the lecture is going to be talking about data structures. So when we finished last Tuesday, I left you with this picture, this roadmap. So this roadmap, it gives a list of many problems. So all of NP. NP, remember, were languages that you can verify if you're given a witness. If you're given a short witness, you can test whether some property holds. So for example, if you're given the vertex cover of a graph with k nodes, you can test whether in fact that graph has a vertex cover of those nodes. Similarly, like problems like subset sum, 3-coloring, ham path, clique, etc., you can all verify answers efficiently if you're given a witness. And it turns out that all of these problems that you can check efficiently, they happen to be as hard as 3-sat. And it turns out that all of these problems happen to be as hard as vertex cover. Now there's one little detail that you need to solve the homework. So I had discussed a vertex cover as a set C such that these properties hold, such that every edge in the graph is covered by one of the nodes. But you can also formulate the vertex cover problem as this. So call VC the set of all graphs and K such that graph G has a vertex cover of size K. And then the problem that you're going to be asked is, given a pair G comma K, does G comma K belong to the set VC? So the answer is either going to be yes or no. In particular, one way to solve this problem is to, in fact, compute a vertex cover, compute the minimum vertex cover, and then see if that minimum vertex cover is size less than or equal to K. If, in fact, it is less than K, then obviously this instance is yes. So if I have a vertex cover of 3 nodes, and I'm asking whether G comma 5 is true, is in the language, then in fact it is. Because there's a vertex cover of 3 nodes, you can just add 2 arbitrary nodes, and you'll have a vertex cover of exactly that size. So this makes these problems easier. Search problems require to produce the answer. Decision problems just require to say yes or no, and so they're conceptually simpler, and they happen to be equivalent. So in the homework, I've asked you to look at the Andrew problem, okay, and that's going to be a problem of the form GK. I've asked you to solve the Andrew problem, so that's if you're given a graph of cities along with the roads between the cities, does this graph G satisfy Andrew's wish, which is to make sure that every town is either has a library or is adjacent to a library? And so to solve this problem, what will you do? I've asked you to show that it is NP complete. So what does that mean? Sure. So that's, in particular, it's going to require 2 steps. The first step is show that Andrew is in NP. That means it is easy to verify. Now, how might you verify that GK, a particular graph in K, is in Andrew? I'll leave that to you, but please answer that part. And second, you want to show that Andrew is as hard as any other problem in NP. So in particular, you could show something like this. Okay? That would be harder than I expect. There's actually a simpler problem. What might you do? Or you might show, for example, vertex cover can be solved with Andrew. And when you get confused, draw a diagram like this. This is going to be your algorithm. What goes here and what goes here. What should this do? So this is going to be a yes-no problem, and this is going to be a yes-no problem. Just to keep everything very simple, you have to put something here, you have to put something there. Both of them are going to be yes-no problems, and you have to do something like this. Very good problem, very good question. How did they show this right here? So what they had to do is show that this theorem right here, which is called the Cook-Levin theorem, they've actually did it with just SAT, but that's Cook-Levin. How does it actually work? This is any problem in NP, right? It's a very generic thing. And so if you take 3102, have you taken 3102? You're in it right now and you cannot answer this question. That's not, I'm not happy about that. If after 27 lectures, you've talked about NP completeness in that class? Okay, all right, okay. So as a very brief overview on how this works. So any problem in L, so L is in NP, so the only real deduction you can make is that there exists an efficient checker. Okay? It's called RL. Okay? So L is an NP, so that means that there's an efficient algorithm which can check whether a particular graph or a particular instance is in the language or not, if it is given this witness. Okay? So what we're going to do is we're going to take this machine. This is a Turing machine. Okay? And a Turing machine is going to start with the tape like this, and it's going to start with X written on this tape, and it's going to start with a little machine like a Turing machine. You know what it is, right? It's a machine like this, and it has a tape and a head, and it decides to move left or move right. That's the most abstract version of a program you can think of. And what this reduction is going to do is say, look, if L is an NP, that means that there's some relation like this, which when you give it an X and a Y that's in the language, it outputs 1. Okay? So what I'm going to do is reduce this thing right here into an instance of SAT. Okay? So if X is in L, that means there exists some witness W such that R of X comma W is equal to 1. And what I'm going to do is turn this Turing machine right here. I'm going to say, well, that was step 1 of the computation. Step 2 of the computation was like this. Step 3 of the computation was like this. Okay? And what I'm going to do is I'm going to take each of these configurations of Turing machines and I'm going to turn it into a Boolean formula. And it's going to be RL of X comma Y is equal to 1 if and only if. Okay? In other words, there exists an input that can make this part 1 if and only if this formula is satisfiable. Okay? Just like when we mapped formulas to graphs, here we're going to map arbitrary programs into basically Boolean formulas. We're going to say, and you can think of it as like this, like, is there, I need to find an input where if I put these bits into the program is going to output 1. And you can think that one can imagine how you take a program and then turn it into a logical formula that says there are assignments to these variables such that this Boolean formula, like think about a hardware, right? You can imagine this program being turned into a hardware circuit, and that hardware circuit you can look at as sort of a satisfiable formula. And if you can find inputs that make the program output 1, you can find inputs that make the formula output 1. That is the general theorem, and one usually does this in 3102 and takes about 3 or 4 lectures to prove that that's how it works. Very nice, clever argument. You should see it one time in your life. So, did I give you enough hints on what you need to do in order to answer that second question? Question? Yep. Okay, so let's look at why SAT is in NP. So a formula is in SAT if there exists an assignment A such that, so in other words, this is basically going to be apply the assignment, let's call this A, to the variables, check if the formula is true. If I were to explain to you why SAT is efficiently verifiable, if I just give you the formula, if you just look at it, it's not obvious whether this is satisfiable or not. But if I said, you know why it's satisfiable? If you make X true and Y true and Z false. So if I give you the assignment, you can efficiently check whether it's satisfiable or not. So now, in this question right here, what could you give me to show me that, in fact, Andrew's wish could be satisfied in America? The cities. You can say, you know what? Andrew wanted a library in every city of America or next to one. So put the first library in Pittsburgh. Put the second library in Boston. Put the third library in Charlottesville. Put the fourth library in Atlanta, etc. You could give me a set of case cities and say, now notice that, in fact, Lynchburg is next to Charlottesville, and therefore it is covered. So you can then go through each of the cities and say, notice, this city is next to a city that has a library. You can efficiently check that the property is true. Yes, efficiently. Das ist NP, yes. Polynomial time, which is what normally in this class, everything in polynomial time is efficient, although in practice, like n cubed would be too much time in America, right? That's like 1 million cities, 1 million cubed. maybe not a million cities, maybe 10,000 cities. Still, it's n to the c would be fine. That's polynomial time. I'm asking, like, you might have a philosophical objection to polynomial time reductions, or you might be saying, I don't know what the rules of the game are. I don't know which one is true, which one is the case. Okay, look, I want to get to something which I think is very, very cool. The dictionary data structure. So a dictionary should allow you to insert elements. It should allow you to search for elements. It should allow you to delete elements. It should allow you to find next elements. Find next, if I give you I, it finds the lexicographically next element in the dict with respect to I. So for example, find next of 17 finds the smallest element in D that is greater than 17. If you actually think about a dictionary, what is the word right after flower in the dictionary? That would be find next to flower. How many of you have taken 2150 so far? Great. So all of you have implemented a balanced binary tree. That's a standard solution for this problem, balanced binary tree. And how much do each of these operations take in a balanced binary tree? If the size of D is n right now, log n, delete, log n, look up, log n. What about find next? How would you do a find next in a balanced binary tree? You basically first find the node, and then traverse the tree using the properties of the tree to find the very next element that's in that tree. Try to find the first guy that's to the right. That's not a precise description, but in general, this can be done in O of log n as well. All of these operations take log n. Let's look at another type of data structure. We have not talked about hash tables right now, but I think everybody has used one in programming at some point and probably is familiar with the interface. How much does it cost to do a find next operation? If I put all of the elements in a hash table and I ask what is the next word in the dictionary after gregarious, how would you find the next element if you had stored your elements in a hash table? It's linear. You could have to scan the entire table that you have and look for the first one that you see. All of these operations, they could be done in constant time, but that is very tricky. Using very standard ideas like open addressing, you're going to get some bucket that's of size log n over log n. And then that's going to make one of your search queries end up being this much time. To get around that, to have actual constant time lookups into hash tables, you have to be very, very careful. This limitation right here, if you know nothing about the universe, if you can accept any sort of input that you have to put in your balanced binary tree, there's a fairly good argument for why one of these elements has to take log n. And that's based on a sorting lower bound. Because if you could do better, you could insert all of your elements into this thing, and then you could just do a bunch of find nexts. You can say find next from 0, and then that will give you the first element, then find next from 1, and that will give you the next element. Between insert and find next, if you know nothing about the world, then one of those operations is going to have to take log n time. Let's say you know something about the world. In particular, let's say you're going to take 64-bit keys. Each person has 128 bits. I just randomly pick them when the accounts are created, and now I'd like to have a dictionary because I'd like to be able to look up a person very quickly, and I'd like to be able to find the next person if I want to enumerate all of the people in some range. So what can we do for this data structure if we know the limitation? What if n is very small? Like let's say n is 1 million. What could you do? Data structures are extremely important. So far in this class we've mentioned a few. In order to solve the minimum spanning tree, we needed what was called a priority queue. That's a data structure. And if we want to do better than the E log V time, we actually needed more fancy data structures like Fibonacci heaps, or what Chazelle calls soft heaps, in order to get his, the world's best deterministic time algorithm so far with the concrete running time. So we've talked about a few data structures. An array, or what's called a bit vector. So what you can do is make a very big vector like this, and just put a bunch of bits. These are bits. Make this one 0 and make this one n, or actually make it 1. And so now to insert an element, all you do is you use bit fixing operations, kind of shifting and anding, in order to find exactly this bit. And for insert, you basically set to 1. Delete, you set to 0. So each of these operations are going to be constant time. Lookups, obviously, you also just go to a particular bit and ask, is it set or not? What about find next? This, unfortunately, is still linear. So we can do all of these operations in order one time, but if I want to find the next bit that's set, okay, I start right here, I'm still going to have to scan bits until I find one bit that's set. So that's going to be the big question of today. How can we do better than a trivial bit vector on find next? What is the trade-off that we have right now? The trade-off is that either we go into the world of balanced binary trees in which everything is taking us log n time. We can do hash tables where all of these are sort of fast, but still find next is slow. But if that's all we cared about, we can just do bit vectors and have all of these things and still have a slow find next. Can we do better than this? Well, what we want to do is find a trade-off. So far, we can get O of 1, we can get 1, 1, 1, and n, right? Or we can get log n, log n, log n, log n. So we can get all logs, or we can get 1, 1, 1, comma n. And now in this lecture, what we're actually going to do is find something that's pretty cool. It's going to be log log n for all operations. And it's going to come back to what we talked about in lecture 2. We solve a problem by solving the same instance that's roughly half the size, right? Question? So the question is, why can't we maintain an auxiliary data structure which keeps track of find next? And if you go through those ideas, the bottleneck you're going to get to is that then you won't be able to insert in order one time. You might have to do a scan to figure out how to update that data structure. What's cool about this idea, it's called a Van M. de Boas queue. You've seen a recurrence like this before, and you've seen it with the bus problem that I've given you. But now I'm going to show you this recurrence applying to a data structure. So the big idea, a data structure for n elements is going to consist of roughly square root of n data structures that handle square root of n elements. So instead of having one data structure hold all of your data, what you're actually going to do is make your one big data structure consist of square root of n smaller data structures that can each handle square root of n elements. In particular, what you're going to do is you're going to have a big data structure like this, and then you're going to have the same data, this data structure right here is going to handle, the universe is going to be 1 through n. And what you're going to do recursively is you're going to have this internal data structure called a map, and it's going to have a universe of size square root of n. And then you're going to have square root of n pointers. Let's call this 0, 1, 2, 3, all the way up to square root of n. And these are going to be pointers to data structures that handle a universe of square root of n. So this VEB data structure, if I was going to do it like this, it's going to keep track of a few things like size, min, and max. You'll see why those are crucial in a second. The base case is if it just has two, if n is equal to 2, then we're going to use a bit vector. And the normal case is we're going to, as I said before, we're going to have a map, and this is going to keep track of each pointer that is not null. So it's going to basically keep track of these indices. Notice that this universe is between, like, let's say, 0 and square root of the n minus 1. And so for that this is going to be a recursive data structure which keeps track of elements in this set. So it's going to only need to handle, of course, square root of n. And these guys are just going to be pointers to VEB instances of size square root of n. At the beginning, they're all going to be null. And then as we add elements to this, we're going to make these elements not null. So let me give you an idea of how one can use a data structure like this. Let's take an example. N is equal to 256. And so square root of n is equal to 16 here. And let's consider the element 55. To put 55 in this data structure, what we're going to do is first write this as a times square root of n plus b. So that's going to be 3 times 16 plus 7. And so to put element 55 in this data structure, what we would do is we would hang a pointer off of this data structure, and we would make another VEBQ of size square root of n, and then we would insert 7 into this data structure. So in other words, each of these recursive data structures are going to handle the first square root of n elements. If that's going to be in your data set, this guy's going to take care of them. The second square root of n data sets, one of those elements is in your data structure, this guy's going to handle them. Right? So this idea of dividing and conquering, it doesn't apply just to tasks that you do, it also applies to how you store data. So remember, this VEB, it's a recursive data structure, so it itself is going to have a map data structure and pointers as well. Let's first do a lookup, and let's try to analyze the running time of a lookup. So if I do lookup I, what I'm going to do is write I as a times square root of n plus b. And now notice that a is going to be less than square root of n, and b is going to be less than square root of n. And then you're going to say, if a is null, then we're going to return false. And otherwise, we're going to return a dot lookup b. So far, we're just going to keep track of keys. But if we wanted to keep track of keys and values like you might need in a real application, you can just add this to the value, and when you return that structure, you can also return any data that goes along with it. The main point right here is, what is the running time of this procedure? So lookup on an instance of size n, it's going to take what? This step takes order 1, this step takes order 1, and what does this step take? It's a lookup on an instance of size square root of n. Now this is a recurrence I've given you in your homework. Yes, that's where the log n comes from, and that's why you get a crazy recurrence like this. N is not the number of elements in your database, in your dictionary. N is the uppermost, it's the number of possible elements in your universe. The rules of the game are the things that you can put into your queue are between 1 and n. That could be like between 1 and 2 to the 64, right? It could be a 64-bit number, so it could be very, very big. If we don't make that restriction, we're bound by the sorting lower bound. So this is kind of crucial. Does everybody kind of see what's happening here with lookup? Let's do something slightly more clever. By the way, I didn't handle the base case here. If size is 0 or this recursive element is null, etc., then you return. This is what I meant by a equal null. Let's try to do find next. Here is where some of the cleverness with this data structure comes in. So what's the problem with scanning? Let's say I wanted to find next 55. Now we know that if 55 were in our data structure, as we said before, since 55 is equal to 3 times 16 plus 7, then we should be looking in this structure right here. But what happens if in fact 56 was in our data structure? We could easily just ask this guy, yes, in fact, you handle all the elements that are roughly around 55. What's the one that comes after 55? Okay, and it would say, yes, in fact, I have such an element. It's 56. Here you go. In that case, of course, we'd have the recurrence like we had before. But how can things go wrong in find next? Yeah, what if 55 is the last element in this bucket? What do we do? Then we go look in the first element of this bucket. Wait, what happens if that bucket has nothing in it? Then we have to go into this number 5 bucket. But if that bucket doesn't have anything, we have to go to the next one. And so in particular, if we were just to use a trivial strategy like that, we would end up, it would be square root of n. We would have to scan this to find the first non-empty bucket, and then we'd do a lookup, we'd do a find next on that one. So we have to get around this problem of scanning. Given that what I've shown you here, what are we going to use to get around the problem of scanning? What's on the screen? We have the yellow dots, and I've showed you how we're using the yellow dots. What are we not using? The green map. You could have said green because there was only green and black and yellow, so that's a good guess with me. This guy right here, that's a recursive queue which keeps track of which of these guys are empty or not. So we have two cases right here. Case 1, if bucket 3 has the next value, bucket 3 does not. And in this case, we can use map to find next of 3, and then find next 3 will tell me the very next bucket that has an element. And now how do I find the smallest element in that bucket? I could call find next on that, but in fact, if we do the recurrence, you'll see that that doesn't work out. What we'll use is just the min. This is where it's very important we keep track of size, min, and max. So what we'll do is just say, I've made my recursive call to find next on this map. It's given me a bucket, and then I return that bucket called min. And if bucket 3 has, of course, the next value, then I'm just going to do find next of 7 on bucket 3. There's one remaining issue, which I'll do in black here. How do we tell if we're in case 1 or case 2? How do we know if that bucket 3 is going to have the next value or not? Excellent. Excellent. Good. And we use max. If bucket 3's max is larger than 55, that necessarily means the next element has to be in that bucket. So we can do the up road. Otherwise, we do the down road. So here's how we'd write this out. So we're going to, again, write both of these things in handle base cases. And just as we said before, if A max is greater than B, then we're going to return the phi next of that thing. Otherwise, we call our map, we find the very next bucket after 3, and return the min of that. And let's again do a recurrence to express the running time right here. And notice this, importantly, this took order 1 time. Okay, this took order square root, this took L of n, okay, and this element right here took f of square root of n, and this right here took order 1. But thankfully, this is in an if-else situation, so again, we're in the recurrence right here of something like this, and that's equal to, as we had before, log n. It gets more subtle. Here's the first way we could do insert. We write these things out like this, and then we basically do a dot map dot insert A and A dot insert B. That's the most straightforward way to do this. We basically put A into here to make sure that it's there, and of course we go to this bucket and insert B as we did before. But what's the problem with this approach? What's the running time of this algorithm? Spend 2 minutes with your partner and write out the recurrence and solve that recurrence. Tell me what the running time of this would be. So this step right here takes order 1 time, right? How much does that map insert take? That's going to be an insert on a data structure of size square root of n. And this insert is going to be an insert on a square root of size n. So this recurrence is going to be like this. Unfortunately, that is going to give us log n, which is too much. So we can't do both of these inserts. And in fact, to your question about what about auxiliary data structures, this kind of what this is doing again. This is maintaining an auxiliary data structure to help you find your next point. But unfortunately, if you do it just like this, it's going to require, updating it requires too much work. So we're going to have to use 2 subtle ideas to get around this. And this is where the insight to this data structure comes. First, how many times do we actually have to insert A there? Kind of to your point, if we know that A is already in that data structure, we don't have to bother inserting it again. And maybe there's a very clever way for us to check if A has been inserted before. What can we do? See, this is kind of like 2 ideas coming together. It's recursion of the bit vector, because this array of pointers, I didn't mention it first, but it's kind of like the bit vector. What we can do is check if it has a pointer here to a recursive data structure. If that's the case, then we can sort of be sure that it has already been inserted before once. We kind of always have to insert this B when we need to insert it. If A already exists, then we can go ahead and insert it right there. So this is kind of the high-level strategy. What we need to make sure is that we only make one heavy insert query. Okay? Whenever we do an insert, we only have to make one real recursive query. The other one we're going to kind of be lazy about doing the work for. That's the big idea. And so here's what we're going to do. It's a very subtle set of code here. The base case before, as we handle if the size of this data structure is totally uninitialized as 0, then we're just going to set the size to 1. We're going to set the min and the max to I, and we're just going to return. So in other words, the first insert to a data structure takes O of 1. The first time you do something, you don't do the recursive work. You just spend this much time. If you already have an element in the data structure, let's skip this first line. Let's kind of look at these next 3 lines, and I'll come back and explain why this first line is there. We're going to do like we did before. We're going to write I as we've done before, and then we're going to check that if the size of A was 0, then we're going to go ahead and insert A into our map, which we have to do. So if A had never been touched before, then we're going to spend the recursive time of doing this type of insert. And then we're going to do the insert of B into A. Okay, and finally, in this recursive call, we update all of these values right here. So let's try to see what happens when I want to claim that we actually only need to do one recursive insert that's going to be heavy. So if A was empty, so if this dangling pointer was a null pointer, then we're definitely going to have to do this line of work, and that's going to cost us insert of square root of n. And we're going to have to do this line of work, but when A is empty, what can we say about that line of work? Because of this special case, it's only going to take order 1 time. We only do this heavy work. If this one was heavy, that means that this one is going to be light because it's empty, and else we're going to spend 0 work on this time and I of square root of n work on this step right here. The way that we've organized this line right here and these 3 lines right here, the insert time is always going to be just 1 recursive call plus some heavy lifting. And now the question is, why can we get away with, when on the first insert, when I is inserted there, we basically don't do any recursive work. We just say, you know what, the size is 1 and I is min and I is max. How can we get away with that? Because next time when we do a lookup or we do any other operation, they were expecting work to be done on these type of things. Well, it also keeps track of, like when we do deletes, we'll have to keep track of size as well, like in order to get into these special cases. So this data structure has a special case when it's 0, a special case when it's 1, and a normal case when it's 2. And that size is going to help us distinguish that. What I was going to say is we also have to change the lookup now, because during a lookup operation, right, if size is 0, then we return false. If I happens to be the min element, right, when size is 1, we don't do any work here. When we insert when size is 1, we didn't put I into the recursive structure. All we did was set it to be the min and the max. And so then, of course, we have to check if I was min, then we just return true. Otherwise, we do the normal lookup. And so the final thing is, why do we do this line right here? So the answer to that question is, let's say that we put in 55 right here. And at that point, when we had 55 in there, all we had was this line right here, that size was 0 for this data structure. So in particular, it wouldn't be 55, but it would be 7, which represents 55, right? I'll put 55 in quotes because this 7 right here represents 55. And then we would have just returned. And the min and the max is, of course, 7, and we just returned. Now, let's say later on, let's say we want to put 54 in. So 54 would be, we need to put a 6, like it's basically calling an insert of 6 on this node. And so size is 0. It's not 0, it's 1. And so we go into this loop right here. Previously, the state of this data structure was basically size is equal to 1 and min and max are equal to 7. And now we're putting a 6 in. What should we do? That's where this line comes in. If min was less than this, we're going to swap this min and max. So now this is going to be, the min is going to be 6, and this element right here, I, is going to be 7. And we write 7 as we should have, and we basically insert on those particular values. So the second subtle idea here is that the very first element, the min element in this queue, is never put recursively in this. The min element is just kept right here, and that allows us to actually be lazy. That allows us to get around this problem of having to do 2 inserts into this data structure and this data structure. We only have a budget to make 1 heavy call on every insert. And so that means the first time we insert something into an empty structure has to be very lightweight. The next time we come back to that data structure, it's going to have some element for which we did no work. And now we have to insert an element. So now this data structure is going to have 2 elements. Conceivably, we could now put both of them recursively in insert, but that would basically cost too much work. That would require 2 recursive calls. And so we always just make sure that the min, the smallest element, always takes constant time to put in this data structure. And that means we only ever have to do 1 heavy insert in every operation. Question? Yes, exactly. You store what used to be the minimum, you swap, so min is now whatever would be 6 right here, and I would be 7, and you do the work on 7. If you were instead going to insert 8, then you would just go through this line again, and you would insert 8. That's kind of the subtle idea here. This data structure involves a lot of interesting concepts. First, you're using recursion, and you're basically taking a bit vector and recursively applying bit vectors at a very high level. And second of all, you need this lazy idea of not having, in order to avoid having to make two recursive calls, which is the problem with any sort of scheme like you're putting forth. You need to have this lazy idea of keeping one element in this special spot min and never having to do too much work for it. And that gives you all of these operations. You can also compute the min and the max, obviously, in constant time. All right. So